Now let's talk about hash functions. So far we didn't talk much about how to make hash functions, right? So we assume that. So now let's talk about how to make it. So before talking about it, if it is the best optimal hash function, then it would have a uniform distributions. That's uniform hash functions for randomly chosen x. So if we pick one identifier, then the probability of the output of the hash function is 1 or b. So it has a uniform distribution. But it's not easy to get this kind of hash functions. So in practice, instead of getting this uniform distribution, we take two steps. First, convert the key into an integer. Okay, that's the first step. And then second, perform some arithmetic operations on the integer. So if it is arctangent, okay, then this is a string. This is not a number. So from this string, we have to make an integer first. There are lots of ways to do that. For example, we'll talk about how to make an integer, but as a simple method, let me introduce this one. A is a 0, and t corresponds to something, and a is a 0, and n corresponds to something. So we can convert this character into the numbers based on the ASCII code, and then just the sum. That's a really simple way to make an integer from a string. So we don't take this approach, but you know what I mean by this. Okay, so you get the idea. So we'll talk about it later. Anyway, let's assume that now our key is converted to an integer. So we have an integer. Then this integer is not evenly distributed, right? So this integer, considering this probability of this integer is not uniform. So we will perform some arithmetic operations, hoping that after these arithmetic operations, the output is kind of evenly distributed. That's our hope. Okay. And let's assume that we have an integer for an identifier. Then what kind of arithmetic operations can we apply? So first one is division. So this one is really popular because when we have a b bucket, then we cannot have a bigger number than b, right? So we apply the modulo operation. So that's division. So this one is most widely used in practice, okay? And then keys are assumed to be non-negative. We can make it, right? So we can make non-negative integers, okay? And then we apply these modulo operations. So when we have a d bucket, then by these modulo operations, then we can distribute the identifier into the buckets, okay? And to avoid bias, then this should be a prime number, but usually just odd number would be fine. So D is the number of bucket, okay? And just the modulo operation is not enough. I mean, applying the modulo operation is not distributing the identifiers evenly on the buckets, okay? So we calculate the integer from the key, and this key is not evenly distributed, but with this not evenly distributed keys, even when we apply this modulo operation, still it's not evenly distributed. So before applying these modulo operations, then we can try some other arithmetic operations too. Then the next one is mid square. The square, the identifier integer. Okay, so we already have an integer for the identifier and then square it, then use appropriate number of bits from the middle of the square. So our key is 22, then we square it. Then it is 484, but in the binary operations, 22 can be represented in this way and the 484 is represented in this way. Then we take just the middle part. Okay, so we take just the middle bits of this squared number, and then this number is actually the bucket number. Okay, so that's good. Then the size of hash table is a power of 2. Okay, in this way, these middle bits depend on all the bits of the key. Okay, so this one is calculated by this number. If we change this number into 23, then this one will be different. Okay, if we change this one into 32, then this one will be different. Okay, so these middle bits are affected by this key number. Okay, that's good. And we are hoping that this one is actually evenly distributed. Okay, that's why we do this, hoping to distribute the keys evenly on the buckets. Okay, and the next one is another simple trick, which is folding. Divide the identifier into several parts and add them. So this one is our integer. Okay, then the cut this number with the size of the bucket. Okay, so basically we just cut like this. So we have 4 numbers, just add them, then we get this number. So again, this number is affected by these numbers, and we are hoping that this number is evenly distributed on the buckets. That's our hope. That's the shift folding. Okay, and there's another variation here, folding at the boundaries. So we have 123, but instead of 216, we actually fold. So we get the 612, and we get the same number, and we fold. So every second numbers will be folded. Okay, so then we can have a little different number, but who knows which one is better. And there is another trick. Okay, so in this case we do a little analysis before doing this. When the identifiers are already given, so we have all the identifiers is fixed. Okay, then it is in the static file, so we know how many identifiers are there and what kind of identifiers we have, and then all the identifiers are known in advance. Okay, so in this case, if we insert a new identifier, then it cannot be applied. And then transform the identifiers into numbers with radix. We learned this radix from the radix sort. And examine the digits of each identifier, deleting those digits that have the most skewed distributions. See, we want evenly distributed keys. So if this one is a skewed distributed, so in this case we have too many 3s, in this case we have too many 1s. We are not talking about just 3 identifiers. We have lots of identifiers. So in the first digit, we have too many 3s compared to other digits. And in the third digit, we have too many 1s, like 211 or 521 or something. And then we can choose this middle digit. So this middle digit is evenly distributed. That's what we want all the time for hash functions. Okay, and then based on this digit, then this one goes to 0, this one goes to 3, this one goes to 2. And we don't have to use just one digit, right? So if we have like 10 digits as an identifier, then we can choose a few digits based on this distribution of the digits. Then we can use them. Okay, again, we can apply this approach when all the identifiers are known in advance. Okay, so now let's talk about converting keys to integers. So it's up to you. You can design your own method, but this is one simple example. Given this key, okay, and then as long as the key is not null, so we are actually iterating this while loop until the key meets the last the null character. Okay, and then the character is actually an integer, right? So we can actually get the number from the character, okay, by this, and then we add them. As I said before, this is really simple example, and then we increase the key. So key is pointing the next character and the next character, and every character will be added to this number, and then we return this one. Or if you want, you can do this, while point key and the number is plus and the key star and times I, okay, and the I increases and key increases and I start from 1. Okay, this is possible. Or I can be I plus 10. Okay, so it's up to you. You have to think about how to make these keys, these integers, evenly distributed. Okay, that's the point. Okay, so now we have really good hash function. Okay, based on the converting the key into integer and some arithmetic operations. So now we have really good hash functions, but still we have overflow problems. Okay, then how can we handle that? So there are a couple of approaches. First one is a linear open addressing or linear probing. So linear probing means we will check linearly. So that's why we call it linear probing. If the corresponding bucket is full, then store X in the next bucket. Okay, so f of X says, oh, X should be here. But when we check this bucket is full, then automatically we just check the next bucket. Okay, and then next bucket until we meet an empty bucket, then we put X here. And if all the buckets are full, then there is an error. We have to increase the table size before we have this kind of situation. That's why we check the loading factor. Okay, if n over s times b is larger than a threshold, then we have to increase the table size. Okay, to avoid this kind of situations. But anyway, as long as we have an empty cell, empty slot, we can actually put a new identifier into our hash table. Okay, so linear open addressing, linear probing is really simple. Okay, just to use a hash function, and if that bucket is full, then go to the next bucket and the next bucket until we meet an empty slot. Okay, good. It's really simple, but in the worst case, we should examine the whole table, right? And it makes some clusters. Okay, let's check the first thing. First, we have a hash table, and first we insert A. Okay, so let's assume that our hash function is based on the character, first character, and then A goes here, and next one is AB. Then a hash function says, oh, it should go to the first bucket, but first bucket is full, then AB should check the next bucket. Oh, next bucket is empty, so AB goes here. And then the next one is B. Where should it go? B, check this one, and B should go to the next one. Okay, and if we insert A, B, C, then where should it go? So hash function says, oh, it should go to the first bucket, but first bucket is full, then second bucket, second full, third, which is full, and the fourth. A, B, C is here. So this is not actually a hash table. Technically it is hash table, but it's not working as a hash table. So every time when we check, it is not the right bucket. Okay, so we have to check. In the worst case, we have to check all the buckets. Let's say this is full, and finally the last one is empty, but if we insert a tangent, then a tangent will be in the last bucket. That's the worst case. Now let's search arctangent. Then hash function will give us the address of the first bucket, and first bucket is not arctangent, we have to check the next bucket. Next bucket says, oh, I'm AB, which is not arctangent, then we should go to the next one, which is C. Then we should go to the next and next, the next. We have to compare all the identifiers. Okay, so that's the worst case. So it is not working correctly, and it makes clusters too. So with these examples, we have cluster here. Once we have a full bucket, then probably we have a high probability to have this bucket is full too. Okay, and if these two buckets are full, then we have higher probability to have this bucket is full. Okay, it means if these three buckets are full, then whenever we want to insert any identifier into anywhere around here, then this one will be full. So once we have a full bucket, then probably we will have a full bucket right after that bucket. So it makes clusters. So it is not using the hash table in an efficient way. That's a really bad idea. So linear probing is simple, but not that efficient. Okay, there is an example here. If you insert this one to 26 buckets with one slot, then you can see what's happening here. Okay. And there are a couple of variations of linear probing. First one is a quadratic probing. So first we check hash functions, and when we have the full bucket with this function, then we use fx plus 1. Fx plus 1 is exactly the same as a linear probing, right? But that's not it. If fx plus 1 is full, the bucket of this f of x plus 1 is full, then next time, instead of checking the next bucket, actually we check the previous bucket. Okay, and then if the previous bucket is also full, then we check if this one is full, then first we check the next bucket. If this one is full too, then we check the previous bucket too. And if this one is full, then instead of checking the next one, actually we jump to 1, 2, 3, 4. We check this bucket. Okay, so we can avoid a clustering problem here. Okay, but still this one is not the best. And there is a rehashing. Rehashing is actually is applying a series of hash functions. So we have lots of hash functions. Then we apply the hash function first, h1, and if h1, the result of this h1 points to a full bucket, then we just apply the hash function 2. Okay, and then hash function 2 might point somewhere around here too. So it's not linear, it's not quadratic. It depends on how you design these hash functions. Okay, then the next one is pseudo-random probing. So next address is calculated by this one. So let's say the first hash function is 2. The value of hash function is 2. Okay, so we check bucket 2, and if the bucket 2 is offlow, then the new address is based on these equations. So A is 3. So we fix this A and the C and the M. M is basically the number of buckets. Okay, then A is 3 and f of x is 2 and the C is -1. So we just implement these simple equations. Then next bucket should be 5. Then we check bucket 5, and when the bucket 5 is full, then we apply this equation one more time. So 3 times 5 minus 1 modulo 307. So now we check 14, and if this one is full too, then we apply this equation one more time, like 3 times 14 minus 1 and modulo 307. And we keep doing this until we find an empty slot. Okay, so this one is rehashing. Actually, Rehashing is more general than this one, right? This one is actually a specific special case of this rehashing. Also, quadratic probing is also a special case of rehashing. But anyway, so these ones are variations of linear probing. And the last one, this one is kind of the best one. Okay, it's a chaining. So make each bucket by a linked list. Linked list again here. Linked list is everywhere. If you don't understand how to use linked list, then I'm sorry. Okay, so how can we use a linked list? So we have a hash table here, and this one is pointing one linked list. So based on the hash functions, so we actually assign an identifiers to one of these buckets. Okay, and then when we assign an identifier, then we start this linked list. Okay, then if we assign another identifier to the same bucket, then we can increase the linked list and again and again. So there's no really overflow problem here. As long as we have enough memory space, then it's fine. So we can increase the linked list as much as we need, right? This is a good way to avoid overflow problem. What is the pros and cons? Advantages is really fast because we don't have to rehash, or we don't have to check the next bucket and next bucket. So it's not linear. So it's really fast, and there's no limit in the number of elements, as I just said. Okay, and then there is a cost. This complex structure, so we have to handle this linear linked list. If we have n buckets, then we need n linked list. So we have to manage all this linked list. It says complex structure, but it's not that complex. Okay, but compared to other hash functions, hash tables, then this one might be a little complicated. Okay, then it requires additional space for a link for the pointers. Okay, so as long as we can pay that cost, then chaining is the best. So generally, the division hash function with chaining yields the best performance. That's the best way. Okay, as I said, after calculating the integer, and then apply some arithmetic operations if you want, and then apply the modulo operations with the number of buckets, and then use a linked list. That's it.